Welcome to lecture 26. In 26, we're working POGIL exercise 11C on page 141. The next few reactions, they don't actually involve the full carbocation. They form a three-member cyclic intermediate. We saw this with this reaction here, 11B, where we used mercury acetate and water, and then we treated with sodium borohydride to produce Markovnikov addition of OH, of water. So we remember this was called the mercurinium ion, and it's a three-membered ring. See how it's a three-membered ring with mercury in the middle, and it's a positively charged. And so we put the delta positive on the more substituted carbon. And the reason why this is important is because in your nucleophile, water in this case, attacks and opens up that ring. We also talked about what if that was methanol as your nucleophile. So if this reaction was done in water, you would get ether. And then sodium borohydride delivers a hydride, which exchanges basically for the mercury. So it's just that will replace the mercury with a hydrogen, and then we have an OH here. Okay, but the reason why I bring this up again is this was a three-membered ring, and you see how it has the delta positive on the more substituted, and this delivers the nucleophile to the more substituted carbon, which is called the Markovnikov addition product. All right, so in part C, we're going to see the other reactions that follow this cyclic intermediate. So the first one we have is Model 1, and we are doing halogenation of alkenes. And this is another reaction you need to get on your reaction sheet. So we have our cyclopentene, and we're reacting this with bromine. And this is a step 1. And it forms this intermediate bromonium. It's called the bromonium ion. And then the other Br here is your nucleophile. And now this is important here because we're showing stereochemistry. So you notice that one bromine is coming at you and the other bromine is going away. So you will have to show stereochemistry here. So if you're filling out your reaction sheet, this is a vicinal dibromide. And the vicinal means they're next door neighbors. Remember, that's German for neighbors when we're talking about that. Okay, so Model 1, we have question 1A. In the halogenation reaction shown in Model 1, what reagent is added to the alkene? The bromine, right? What is the functional group of the product that is formed? It's vicinal dibromide. What does vicinal mean? I wrote adjacent carbons. You could also write neighbors. 1D. Compare the bromine atoms in the product. Halogenation occurs, did you say syn or anti? That bromine's coming at you and that one's going away. So I would write anti. And that's stereochemistry. Okay, question number 2A. In general, an alkene is Did you say electron rich? Remember we said it was the nucleophile, the double bond there. The alkene would act as the nucleophile, 2B. If an electron-rich species approaches one end of the bromine-bromine bond, discuss what effects this would have on the dipole. Use delta positive and delta negative signs on the bromine to illustrate the induced dipole. So because this is very polarizable, bromine gets an induced dipole. I tell my students this is kind of like when you take a balloon, and if you try to put a balloon on the wall, it doesn't stick. But if you generate some static electricity, you add electrons to it by rubbing it on your hair, and then you stick it to the wall, what happens? Those electrons kind of shift on there, and you actually create this induced dipole. And so when something's approaching, like this electron-rich right here, so this is electron-rich cloud, and it approaches, these electrons start moving more towards bromine, and then that's how you get this delta positive. So that's the induced dipole. 3A. In step 1, identify what bonds are being broken and formed. If the bonds broken are your reactant side, and it's going to be the Br-Br bond is broken, and the carbon pi bond is broken. And what's formed? The carbon Br and the carbon Br bond is formed. And that's that cyclic three-membered. Draw curved arrows for step 1 to illustrate electron movement. Okay, so the electrons, these two electrons are going to go towards the induced dipole here. And then those electrons will leave to go with bromine. And that's how you get this bromide ion. Okay, bromine's really big. That's another thing too. You'll notice that these three-membered ring cyclic intermediates, I think it's largely because of the size. Mercury is big, bromine's big. Okay, so where must the electrons come from to form the second CBr bond in the cyclic bromium? It actually comes from the bromine. Like I said, it's just big, and that's why it's a partial positive. The cyclic bromonium ion results from forming a second carbon-bromine bond. If this bond did not form, the cation below would have resulted. Compare the stability of this cation to the cyclic bromonium ion. Which would you expect to be more stable? So this I'm just going to put here for your 3C. It does form, and it prevents a full carbocation. So you don't get a carbocation. So you don't have any rearrangements. And that's what's nice about these cyclic intermediates. Okay, 4A. For step 2, label the nucleophile and electrophile and draw curved arrows to show the electron movement. Okay, well, where your negative charge, that's your nucleophile. And that's going to go, and you see that it's going to, and you might as well whenever you see the positive here, go ahead and make that a delta positive and the more substituted. And then it comes to the more substituted, and it opens. And you have to, and you don't have to even kind of worry about this, except you have to show that it's anti, using your dashes and wedges. Okay, so that's the thing. There's your electron flow movement. You see the two electron flow arrows. And then you want to say that it comes from the opposite side. So this is going to be stereochemistry. And it's a backside attack. It's like SN2. And you show this with your dash and wedge. So I'll be looking for that. Okay, so when bromination is conducted in water, a halohydrin is formed as shown below. Okay, so when you get the halohydrin, which we're going to do, this is another reaction sheet, so you need another reaction. Okay, so you need to get this reaction in another reaction sheet. And this is when you add bromine. Bromine is an orange liquid, okay? And you add it with water. So what happens is, this is your nucleophile. This has an induced dipole. So that's going to be your electrophile. Electrons go here, electrons go there. You have to draw, you do need to be able to draw this mechanism. So you want to show your three-membered bromonium ion. So that means it's a three-membered ring with the bromine. You can even write on there bromonium ion. And then whenever I get this three-membered delta positive or positive ion, I put my delta positive there because I'm looking at that and saying, okay, that's more substituted. So now my bromide would come in. But now we're swamping it with water. Okay, so you also have a lot of water, which is also a nucleophile. So this is going to be in water. Okay, so now water can come and attack here. Backside attack. And then you just show this with the OH here, CH3 there, and then the bromine has to go down. So the important thing is that you have one of these going up and one going down. I don't necessarily care which one's which, okay? And they're showing you that you can get it from the one face or the other. No, it's saying it's not formed. Okay, so this is the only product that's formed. Okay, so the reason why is because of this delta positive is drawing electronically that nucleophile to give you the OH formed, and that's your A compound. So what two groups make up a halohydrin? The halo, the halogen, and the hydrogen is OH. So that's a halohydrin. Compare the stereochemistry of these groups. The addition occurred OH and Br, anti. The cyclic bromonium ion is also the intermediate in the halohydrin formation. What reagent acts as a nucleophile that adds to the cyclic bromonium ion? Did you write water? It says use curved arrows to show the attacking of the cyclic bromonium ion. What two possible halohydrin products A and B are shown? What is the relationship between these compounds? These are stereoisomers. They're RR and SS. So you can actually go and assign the stereochemistry. But halohydrin A is the only product that's formed. In order to form the halohydrin A, the water attacked from the more substituted carbon. So we call this the Markovnikov. So this is Markovnikov addition. Okay, so our next question is 5E. Since only product A is formed, the reaction is said to be regioselective. Okay, regioselective is Markovnikov. As a group, discuss why attack is regioselective. That's because it's delta positive. It's electronically driven. It draws in the nucleophile to that carbon. Is the regioselectivity in the reaction controlled by electronic factors or sterics? I would say electronically. Okay, is the mechanism SN1 or SN2? It's backside attack, anti. SN2. All right, so now we're going to do model 2. This is another reaction. We're going to talk about epoxidation of alkenes, and then we're going to talk about, I think you got about 4 reactions in this model. But the good news is this is going to wrap up the reactions for electrophilic addition for chapter 8. Okay, so now we're on model 2. This is epoxidation of alkenes, you'll want to get out another reaction sheet for this reaction. You're reacting this with peroxy acids. So this is a peroxy acid, and we'll give you some peroxy acids to look for. They're showing you the transition state here. You will not have to draw this. So, transition state. You do have to be able to draw your product though, which is an epoxide. Epoxide is a three-membered ring with an oxygen in the middle. And then the other thing you get is carboxylic acid. So, it is this oxygen that gets delivered. And so these two oxygens here become just the carboxylic acid. So this would be an acidic type reaction. All right, so 6A. In epoxidation, what atom is added to the alkene to form the epoxide? It's the oxygen atom. What reagent in Model 2 reacts with the alkene to form the epoxide? The peroxy acid reacts. And a lot of the time you're not going to see just R. You're going to see, you might want to put this in your, you might see something like this, or perbenzoic acid. Sometimes you have perbenzoic acid as a common one. My favorite, metachloropurbenzoic acid. I think it smells like freshly cut green grass. So metachloropurbenzoic acid. You can think of that MCPBA. What is it? It's a song. Okay, so those are some examples of peroxy acids, and you'd have to recognize that. In the presence of an alkene, you're going to get an epoxide. So the oxygen-oxygen bond of a peroxy acid is weak. You could actually go look that up in your homolytic cleavage. Okay, so it's that bond that's very weak and can break heterolytically as shown below. Draw ions obtained from the cleavage expected from the arrows. So your reaction here they're showing you to draw this and then a plus. And then they show you another one that you're supposed to draw. The electrons were to go this way. And what does that look like? Okay, compare the two anions above. Which would be the better leaving group? Well, obviously the better leaving group would be this one because it's stabilized by resonance. And you could do that. Okay, so the first one, and that would give you a plus OH. Based on your answer above, predict which oxygen of the peroxy acid is likely to act as the electrophile. Okay, so obviously this would be your electrophile, oxygen. Circle the oxygen in the peroxy acid in Model 2. Oxidation occurs by forming the transition state formed in Model 2. The mechanism is concerted. Okay, there's not stepwise. So there is stereochemistry, and it does do syn addition. So a lot of times you have to show that the epoxide added on the same side. And the reason why that's important is, I'll show you, what if you get, so let's say you have a cis compound and you add MCPBA. A lot of times this is in dichloromethane, which is a nonpolar solvent. So if you have cis, cis is going to remain cis. Okay, so that's what that means. If you have trans alkene, then you're going to get trans. Of course, you can make this like that, but you'll maintain your stereochemistry. And that's what it's going to show you here. So does the mechanism support syn or anti-addition? It's going to add to the same side, so it's going to be syn. And then question number 8, which is talking about what we just looked at. The geometry of the alkene is retained in epoxidation reactions. Okay, that's what we're talking about, geometry retained. So that means cis stays cis and trans will become that trans. Okay, so this means if two groups on the alkene were cis, they would remain cis in the epoxide product. In the following reaction scheme, circle the products that clearly show retention of alkene geometry epoxidation. Okay, so here we have this compound. And we're adding RCO3H, which is a peroxy acid. Okay, so the ones that I would circle are the ones that show the R group on the same side. So that's the second one. And then the other one's anti. The other one doesn't show any stereochemistry. And then the very last one shows the R on the same side. So those are the two I would circle. And then 8B, draw the products formed on reaction of the following alkene with a peroxy acid showing syn addition and retention of stereochemistry. So I'm going to go ahead and write out the phenyl. You'll want to get this in your reaction sheets because you'll want these reactions for organic 2. So we have the phenyl on opposite sides here. This is a tri-substituted alkene. We're reacting this with our, I'm just going to go ahead and put MCPBA. You would use this in dichloromethane. And we see that our bigger groups, this is trans, because you're comparing, when you compare these two, the phenyl is your larger, so that's number 1. And then when you compare these two on this side, your phenyl is number 1. And so this is trans. And so you would want to show this like so, where you have things on your dash and wedge. I will just do both of these here. And then so here you'd want to put your phenyl. So write phenyl and a hydrogen, and you want phenyl and a CH3. And here you want phenyl and a hydrogen, and you want CH3 and phenyl. And that's how you show your retention of stereochemistry. And now we're going to talk about epoxide opening. So once you make your epoxide with the peroxy acid, then you can open up your epoxide. And if you open it up in acidic conditions, you're going to get something different than basic conditions. So that is what we're going to do with Model 3. So model 3 is epoxide ring cleavage. You're going to see these are different in acidic conditions versus basic conditions. So now that you know how to make an epoxide, this is kind of like a new functional group for you. So this is acidic conditions. See, you have your hydronium. Step 1. So step 1, oxygen likes to get protonated. So oxygen is going to get protonated. That activates it. So it gets a positive charge. This is a protonated epoxide. And now we have water. And then in step 2, we're going to get our diol product. And you'll see that that's anti. I'm just going to draw like that. 1,2-diol. Okay, so number 9A. Consider the reaction of an epoxide with acid shown in step 1 of model 3. The CO bonds of the epoxide are polar. Okay, carbon, oxygen, that's a polar bond. If polar, label each carbon with a delta positive and oxygen with a delta negative. So this is positive, this is negative. This is positive, this is delta negative. Okay? So 9B. An acid donates a proton. So this is your acid that's going to donate a proton. What atom of the epoxide will be protonated? The oxygen will. And it says draw curved arrows to illustrate the protonated oxygen. So these electrons will come here to take away that hydrogen, and then those electrons go to the oxygen. And that's how you get your water here with its 2 electrons. And then we have hydrogen covalently bonded to the oxygen, making it a protonated epoxide. Now, do you notice that that's a 3-membered ring with a positive charge? So this is where you're going to want, anytime you get a 3-membered ring, let's just change one of these. Okay, since if you're doing this for your notes, let's make this a CH3. Okay, let me show you why. Okay, so if this is a CH3, and I'm going to make this a CH3. Okay, because whenever you do that, now you need to put in your delta positive, and you would put your delta positive here. Okay, so anytime you have a protonated epoxide, then you need to put in a delta positive on the more substituted carbon. And this is going to lead your electrophiles there. Okay, the protonated epoxide is going to be more reactive, okay, than a neutral one. Okay, step 10A. In step 2, the protonated epoxide forms the 1,2-diol. What compound acts as the nucleophile? The water is going to act as a nucleophile, and in this case, the water is going to add here. Okay, so the water's adding to the more substituted carbocation. The product is, do you see the OHs? One's coming at you and the other one's, that's trans. That's because this is like an SN2 attack when you open up that 3-membered ring. Compare the second step of the epoxide ring opening to the second step of the halogenation of alkenes. Note the similarities and differences in the reactions. Okay, so what's the similarities? Okay, you still have a 3-membered positive ion ring intermediate. They both have a nucleophile that will do backside attack on the three-membered ring. And therefore you have anti-stereochemistry. Now the difference is you're getting a halohydrin versus a diol. So you're getting a different product. Okay, so what about 11D? Predict the product formed in the reaction conducted in methanol instead of water. You will want to get this on your reaction sheet. So if you have this, this is the product. Predict the product. So this would be the product. So I think there's a typo here. So let's I will give you the reaction. You'll get something like this. Okay, let's do this 2 steps. Here you go. Step 1, you reacted with MCPBA and dichloromethane solvent. And then step 2, you react this with acid and methanol. Okay, so the first step, the first product you would draw is, let's just draw this with CH3. Let's do my whole reaction. Okay, there's your epoxide, CH3. That's from step 1. Okay, then step 2, this would get protonated. So the first step, the next reaction, you're going to get protonated epoxide. And you'd want to show this because it shows your three-membered ring. Now we can put in our delta positive for the more substituted carbon. That's going to direct your nucleophile. This is your nucleophile, methanol. It's going to come there and open this. And then your product will be, if this comes from the top, then we would write this like this, OCH3. This would be at the bottom, and then this would go there. Okay, so that would be a hydroxy ether. Okay, 11A. If the epoxide is not activated by reacting with acid, then any nucleophile can react with the neutral epoxide. Must be a strong nucleophile. Okay, so you know strong nucleophiles are going to have like a negative charge. Okay, so this is the basic. This is going to be under basic conditions. So strong. Which atom of the epoxide is most likely to be attacked by a nucleophile? Okay, obviously it's going to be the carbon. It's going to be the delta positive, because you got delta positive during negative carbon. Draw curved arrows to show how the nucleophile attacks an epoxide in the reaction below. Now I'm going to show you this, but I'm going to also put a methyl on there. Okay, so I'm doing 11C, but I'm going to use this example instead. So you have an epoxide, and then let's put a methyl group there. Now, if you have a nucleophile, let's just do a nucleophile. Let's say this is your nucleophile. So you would need to recognize that that's a plus. That means this is a negative, okay? You don't have acidic conditions. This would be considered basic. You don't have a three. There's no three-membered ring, okay? So no positive and no delta positive carbon. So this is going to be sterically driven, kind of like an SN2. So this nucleophile is going to go to the least substituted. So it's going to go to the least substituted carbon. And so when you draw that product, you still have to show your stereochemistry. And now it's the OCH3, it's coming from the top. And then that would make this anti-OH and swing this up, CH3. The important thing is that you have anti with your oxygen nucleophile and your oxygen. Oh, you could just go ahead and do your dial. What's happening here? It's always easy to pick up a hydrogen in solution. So I'm going to do this so I don't get a lot of questions here. When this comes in, OCH3, and this is O minus, and this is CH3, this insolvent, this would just pick up, there's always going to be a little bit of methanol around, so it can just pick up that, and that's how you get the proton there, the hydrogen, and then it reestablishes your nucleophile. So that's just a proton transfer. It's showing you here too that they add water. So you also can add water in a separatory funnel. And that's called, in the organic lab, that's called quenching. So if you quench a reaction, you add water to it, and you're donating that hydrogen for the transfer. Okay, so that's what we're talking about here, and the reinforcement that with 11D. Consider the unsymmetrical epoxide shown below. On reaction with a nucleophile, which carbon would most likely be attacked? So here we have this epoxide, and they're saying with just a regular nucleophile like sodium cyanide. So when you see this, you can make sodium positive, cyanide negative. Which carbon would be most likely attacked? It would be the less hindered. So the less substituted carbon. Because the epoxide is not protonated, a partial cation is not likely to be formed. Is the regioselectivity in this reaction controlled by electronic or sterics? So this would be sterically controlled because there's no positive. Draw the expected product. So if you were to do this, you could just keep your CH3 here, CH3 there. I would just draw my OH and then CN. And that would be your product. All right, now we're going to do model 4, and these are new reactions. So I think we have about 3 more reactions for this chapter. So model 4, I would recommend you get 3 reaction sheets out. Okay, this is going to be oxidation and oxidative cleavage. Now, when I do oxidation reduction reactions, I don't do electron flow arrows. It's more of a loss and gain of electrons. We talk about this in chapter 10 or 11. So it's usually organic 2. We talk about oxidation and reduction. So when we do, I won't ask you to draw the reaction mechanisms. You can draw intermediates though, but you don't have to draw the electron flow arrows. Okay, so, and then we treat this with water and sodium hydroxide. and we're going to get a diol. Now, how does this diol look differently than the diols we just made in Model 3? They're also called glycol. Notice that the OHs are both on the wedge, so they're both coming at you. Okay, now if we add permanganate with heat, okay, what happens? You actually cleave that bond. So 1, 2. I have to number them all. Okay, this is oxidative cleavage. So the difference is when you use permanganate at cold temperatures or room temperatures, it's very mild. But if you heat it, then you can actually cleave that double bond. And a lot of times what I do is I just draw a little line through there, and then here, I'll even draw it right here. So I draw this here, and then I do my eraser, and I draw double bond there, double bond there. You see? And then you make that an OH because it has a hydrogen there, and the hydrogen becomes an OH. And you don't have a hydrogen here, so it has to stay. That's a ketone. That's a carboxylic acid. Okay, that's a diol. So those are two reactions that you need to get in your reaction sheet. All right, let's answer question 12a. For the oxidation reaction shown in Model 4, what is the product formed? Do you write a glycol? Okay, a diol. The stereochemistry of the product is, what did you circle? Cis, stereochemistry. Consider the cyclic intermediate. Okay, here's our cyclic intermediate. This is called a permanganate ester. How does the stereochemistry of the intermediate dictate the stereochemistry of the product? Now look, if you look and you drew the manganese, potassium permanganate, it has like an oxidation state. How many bonds are there to manganese? 1, 2, 3, 4, 5, 6, 7. That's a +7. Okay, and you see how two of these oxygens have bonded with the double bond here. Okay, so those two bonds. Now how many bonds are there in manganese? 1, 2, 3, 4, 5. That's +5. So you see how you have, if you've gone from +7 to +5, that's a reduction. So you just reduced manganese. And in doing so, you added 2 oxygens to these carbons, so you're increasing their electrons. That's oxidation. Anytime you add oxygen to carbon, oxidation, where do you think the word came from? You know, it's really actually more of an organic thing than it is an inorganic. That you do in Gen Chem. You're adding oxygen to carbon. You're oxidizing the carbon. Carbon went from having hydrogen to oxygens. Okay, so that's oxidation. You're adding at the same time. This is concerted, and that's why we're going to have stereochemistry, and it will be syn. Okay, on the same side. 12D, oxidation can concur also. So you're also going to see, especially in sapling, a reagent using osmium tetroxide and hydrogen peroxide. Osmium tetroxide also can do this, and osmium looks like this. It's more expensive, costs more money, and it is more toxic than permanganate. Would you expect a similar cyclic intermediate? Yes. So you can use that reagent as well. Predict what products of the following reaction. Okay, so what did you do? You can add this to your reaction sheet. Potassium permanganate, hydrogen, water, and base. Okay, so this is mild, there's no heat, and I would just put my OH here, and you can just do an OH there just to show that it's stereochemistry. Okay, for 13A, for the oxidative cleavage reaction, okay, so we're looking at the oxidative cleavage reaction, which is this one. What reaction conditions have changed in order to get the cleavage product? Heat. Carbon 1 of the alkene formed a, carbon number 1 formed a ketone. Carbon 2 of the alkene formed a, would you circle carboxylic acid? What is the difference between C1 and C2 of the alkene with respect to the substitution? Well, your substitution pattern here is, you could say it's tri-substituted. That's tri. And then number 2 is di substituted. I basically look to see if there's a hydrogen here. As a group, determine a rule for how differently substituted alkenes are oxidized. So if there's no hydrogen, I mean, you just basically, I would do this. You just add oxygen here. And if there's a carbon, you add the carbon. Okay, ketone cannot oxidize any further. If you have a hydrogen here, that hydrogen can get replaced with an OH, and so it can go further. So oxidation, as long as there's a hydrogen, you decrease the hydrogen, you increase bonds to the oxygen. So a hydrogen can get also oxidized to carboxylic acid. Okay, F. Predict the products for the following reaction. Okay, obviously we're going to cleave this. We have heat. Alright, so what I like to do is I like to just go like that. And then I redraw. And you see that first one has a carbon and a carbon. So it's going to be a ketone. And then this other carbon, I put in the hydrogen. So I can go all the way. There's a carbon there. And that hydrogen gets replaced to make a carboxylic acid. So those are your products. Number 14. Okay, this is a new reaction sheet. This is your last reaction of this chapter. I know you have a lot. This is ozonolysis. It's also in your book. And it uses ozone is one, and then you cleave the ozonide with, sometimes you'll see it as DMS, and that's dimethyl sulfide. Okay, you can also see it as CH3,2S. Okay, and that will actually, so if you did your ozone, ozone is our friend, right? It protects us from the sun. So this is the Lewis structure for ozone, O3, and what's going to happen is you're going to deliver 2 of these oxygens to the carbon-carbon double bond, the alkene. So they're going to go to the alkene, And then the other oxygen is going to go to the sulfur, and this makes a compound, which is a this is a solvent, DMSO, which is dimethyl sulfoxide. It kind of smells like a pig. It's kind of stinky and really thick and oily. But this is a polar aprotic solvent. It has a high boiling point. Okay, so that's why you got to have DMSO to take the other oxygen away. Now, this is my favorite cleavage reaction. And if you've ever worked with an ozonator, we used to have an ozonator on a cart, and I would have my gloves, my nitrile gloves, and I would be working with the ozonator. And the weirdest thing would happen, I'd look and my gloves would just disappear. So it reacts with the gloves and goes up into the atmosphere and gas. And I know it's really bad for you, but it smells really good. So anyway, that is ozone. So what happens here is we're going to cleave this, and this time we're not going to get a carboxylic acid, okay? So this time we get to keep our hydrogen. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So our hydrogen stays. So it keeps aldehydes. Okay, so you got a ketone and an aldehyde, so that is what's different. And that's what you see in 14. Compare the product of the ozone reaction above to the oxidative cleavage product in Model 4. What is different? So the C2, so we call this C1, C2. The C2 in permanganate becomes a carboxylic acid, whereas the C2 in the ozone becomes an aldehyde. Determine a rule for how differently substituted alkenes are oxidized with ozone. So disubstituted or trisubstituted alkenes, you could say trisubstituted alkenes, you could say oxidized to ketones, the same as in permanganate, but disubstituted alkenes are oxidized to aldehydes, whereas they're oxidized to carboxylic acids in permanganate reactions. All right, now work C. All right, so we got ozone and we got DMS. All right, so you want to just do that. And we're going to add that there. Is that really any different than the other one? Not much different, is it? Okay, so that is your product for that. Now, looking at your additional problems, I really like it when you have to fill in the boxes. You should have some book problems like that, and you can expect to see that on your quiz. So you should be able to work all of 15, 16. I want all the structures. I want all the reagents. And then I want you to box in your answers. Okay? If the reaction is supposed to be syn or anti, there's stereochemistry, then you need to show that with dashes and wedges. So then I know that you know which reactions have stereochemistry versus not. Good job.